if you look at the previous problems, we'll actually find out that you can even use some additional softwares to test if your answers are correct. For instance, the software I shared with you, GeoGebra, Classic. You can test if your answers were correct or actually wrong. So you usually type this. Let me just show you now. So what you do here, you just say GeoGebra Classic. Let's say you check something like this, and then the first one you can see it is there. And then after that, you're gonna type the function y is equal to that, or f of x. I usually like to use y. For instance, if you look into this function here, GeoGebra Classic plots it in a very nice way, and it can even to check your answers, you can see that at some point there the function is actually from 1 here. Look at 1. So when x is less than 1, or x is from negative infinity up to 1, you can see that the function is actually increasing, and then arrives there. And then from 1 and then up to 3, you can actually see that the function is actually decreasing all the way. And then from 3 and all the way up, you can see actually the function is actually increasing. So you can use these functions, and you can even see concavity here, that the function is actually concave down from here and all the way down, and also from here it concaves up, and also the function is actually increasing up until it arrives there, and then it starts decreasing until it arrives there, and then start increasing all the way there. So at this point here, you can even see that you have a local max, and then here you can see that you have a local mean, because this point here is actually the smallest of all the points that are in its vicinity or in its neighborhood. So all these points above it, and also this point here, you can see is a local max, because all the points that are close to it actually are below it, so it's a local max. And also if you look at this function here, you can see that it is a nice function here that is going up and going down, and you can see that we are actually having a local max there. And if you are typing this function y is equal to len, you can see that this function is decreasing all the way down there, and also starting here it also increases like that. And also in between these 2 points, you can see that the function is actually not defined. Even if you actually zoom it out, you can see that there will always gonna be that gap all the way down. This function is not going to be defined at all. So at this point and at that point, those are some of the interesting points. But what is important, can you tell something? So this is one of the ways whereby you can test your answers if you are having some certain answers in your TAT, and also some of the things that you can actually think about. So just for you to know, so that you can test your answers. So the second question was based on the second question here. So the second question was saying, in each of the following functions, find the intervals where the function concaves up and where it concaves down. And then the second one is saying, use the second derivative test to classify the critical points. I want us to actually answer these 2 questions and then separately. So we are actually having the first function, which is we have f of x is equal to x cubed minus 3x squared and then plus a 4. And then once you have this, now you wanted to find out where is it concave up and where it is concave down. What is important here, concave up, we said that this is concave up and this one is concave down. And when a function is actually concave up, we know that the second derivative must be equal to, must be greater than a 0. And then when the function is actually concave down, you want the second derivative with respect to x to be less than a 0. So those are the 2 distinctions. And also, if you are having the second derivative equal to 0, so you will actually end up finding the point whereby the function is changing from concave up to concave down, or from concave down to concave up. That is the point whereby you will end up getting by setting this equal to a 0. And we said that this point is the point that we call the inflation point, or the point of inflection. So let us solve this question here and forget about theory, because we did that in the last couple of lessons. So here, in order to actually talk about concave down, we need the second derivative. So the first step here, remember that we're still dealing with Roman figure 1. So the first derivative with respect to x of this, you bring the 3 down, you have an x, and then subtract a 1, so you have a 2, minus 3 times 2 is going to be 6, and then you subtract a 1, and then this will have the first derivative being equal to a 0. And then the next thing here, we want to find the second derivative with respect to x, or the first derivative of the first derivative. So what is the derivative of this? You bring the 2 down, we'll end up having 6x, we subtract a 1, so we have a 1 there. And then here we'll have minus 6, or simple 6 times x minus a 1. And then the next step is you want to set the first derivative equal to 0. So you want to have 6 times x minus 1 equal to 0. This simply means that, okay, after we've done that, I'm going to divide by 6 on both sides. This 6 and this 6 will cancel out, which means now we'll have x minus 1 equal to 0. And then I'm going to take this 1, which was negative this side, to the other side, so it's going to be positive. So we'll end up having x is equal to a 1 there. So this is one of the points that are making the second derivative equal to a 0. So we are having that now. So what are the values of x that are making this undefined? Of course, this is actually a polynomial, so it is defined everywhere. So this is the only point that we actually have. So this point here is the one that we place it in a number line, and the number line is moving from negative infinity to positive infinity, and that point is going to be a 1. So I pick a point that is less than 1, which is a 0. I pick a point that is bigger than 1, which is a 2. I take this 0 here, I plug it in the second derivative. So if I'm plugging a 0, 0 minus 1 is going to be a negative 1. Negative times a positive is going to be negative. So we have a negative here. And then I take this 2, I plug it in the second derivative, and then when I'm plugging it there, 2 minus 1 is going to be 1, which is positive. Positive times a positive is going to be positive. So we have a positive number here, so that we are having a positive number. This one here, we don't include it. Why? Because at this point there is nothing that is happening. There's no concave up or down. We just know that concavity is changing at that particular point. So the next thing that you do, you can see that from negative infinity up until you arrive at 1, you can see that f concaves, because it's negative, so it concaves down. And then if you look into this point here from 1 up to positive infinity, you can see that we have a positive. So because we are actually having positive, f actually concaves up. So that is actually what is important here. You can even use the same principles that I was using here, that if, let's say, you try and deal with this function fairly. This function here is here. You can see that from negative infinity up until you arrive somewhere at 1, we have a concave down, and then from 1 all the way to infinite we have concave up. That is what we are actually doing here. So I'm not smoking some nyaupe, I'm actually on point. So that is what is important here. Another thing that I wanted to, so this question you have answered it, so I can say that this question has been answered. So Roman figure number 1. Now I want us to talk more about point of inflection. So if we wanted to find the point of inflection, you must know that the x coordinate is when the first derivative is equal to a 1. So we are going to have 1 there, and then we take this one and we plug it in the original function. So when you're plugging it in the original function, you will end up having a 1 cube, and then after that you subtract a 3, and then you have a 1, and then you raise it to a 2, and then you say a plus 4. So at 1, 2, when x is equal to 1 and y is equal to 2, that's where we are having point of inflection, or inflection point, point of inflection, or inflection point, or a flex. So this point here is the point of inflection, and you can even see here when I was drawing this that at 1 you can see that we have 1 and 2. This is the point whereby this point is the one that we call it the point of inflection, because we were on concave down and now we're moving to concave up. So that is that point, or point of inflection. Of course, the question did not ask this thing. I just wanted to tell you so that you know that when you want to find the point of inflection, you need to find out the second derivative, and then after that you set it equal to 0, and then you get the x coordinate, and then that x coordinate you plug it in the original function. So that's how you will end up getting a point of inflection, and a point of inflection have an x and y coordinate. Now let us move to Roman figure number 2. So Roman figure number 2 is saying something that is very nice, and is saying use, now let me show you so that I don't have my own thing here. Use the second derivative test to determine or to classify the critical points. So now, how do you find out the critical points or the critical numbers? So the first thing here, to find the critical numbers, you need to find first the first derivative with respect to x. And if you notice here, we already found the first derivative as 3x squared minus 6x. So this one is 3x squared minus 6x. So we're having the first derivative. The second thing, you want to set it equal to 0. So we wanted to set it to be 3x squared minus 6x. Equal to 0. In other words, I have a 3 and a 3 contained there, and then I have an x and x, so I have an x, so 3x is common. Once 3 is taken, there is no 1 here, and then here's 3 divided by 3 is 1, and then x squared divided by x, so we'll end up having an x minus a 2 here is equal to a 0. And then of course, for this thing to be equal to 0, 3x must be equal to 0, or x minus 2 must be equal to 0, which means that our x must be equal to 0, or x must be equal to positive 2. So we are having this thing here. We're having this or that. These are the critical numbers. In other words, the first values of the values of x that make the first derivative equal to 0. These are the points whereby the function is not increasing and also is not decreasing. The point of inflection is the point whereby the function is not concave up or down, is changing in between. So I want you to get those. And then once you have these points, you want to find out what are the values of x that are actually making this one undefined. You find out there are no such values, right? So because we want to classify the critical points, when x is equal to 0, the question is, what is f of 0? When x is equal to 2, what is f of 2? So those are also important points, because we want to classify, is it max, is it min? So that is what we want to find out. So if I were to plug in here 0, and then here I am also getting a 0, what will I get? I'll end up getting a 4. Where is the original function? So I'll plug in a 0 and a 0. This is 0. I will end up having a 4. So that is what we are getting here. I have a 4. But if I'm plugging in a 2 here, I'm going to plug in a 2. And then here I will end up having a 2. And then here I will end up getting a 0. So this one is actually a 0. This actually means that we are having a point which is 0.4, and then another point is actually a 2.8. a 0. So is this a local max? Is this a local mean? But now, instead of using the first derivative test, in other words, the number line of the first derivative, we want to use the second derivative test. What is the second derivative test is actually saying? We talked about we talked about this one. This one is actually telling us if we're getting concave up or concave down. So what is left for us is this nice thing here. So if, let's say, I have concave down like this, in other words, the second derivative with respect to x is actually less than 0, I will end up having concave down. And if I'm having this, the second derivative with respect to x is greater than a 0. So if the second derivative is actually less than 0, this point here is supposed to be the max. And also, if I am actually having concave up, at this point here, any point that is here will end up having a mean. So if I'm looking at x here, x equal to 0, and I'm actually coming here and looking at this number line, you can see that 0 is a number that is less than 1, and any number that is less than 1, we are actually having concave down. So we have concave down. Concave down is actually telling us that this one here is supposed to be a local maximum. So we have a local maximum because we have a concave down for all the values that are less than 1. So we have a local maximum. For values that are bigger than 1, we have concave up. In other words, we're supposed to end up having a local minimum. I hope you can actually see what is happening here. Minimum. So that is what we use the second derivative test. That what is important here, we can see that actually this value here falls in the interval. So 0.4 0.4 is somewhere in this interval whereby the function concaves down. So we have a local maximum, and 2.0 actually falls in this interval where we're having f concave up. So we are actually having a local minimum. That's what we actually wanted to solve with this particular problem of ours. And another thing that you can even look at here, we had this problem here. If you look into it, we had this, and you can see that when you're actually at 0, 0 and 4, we have this is a max, and at 2 we have a mean, exactly as we expected. And here we have a concave down, here we have concave up. That's what we expected. So at least now we have an idea of what is happening. Let's look at B. What is B saying? B is saying we are having f of x, and f of x is equal to x to the power 4 minus 4x squared. And then once you have that, of course, we wanted to first find out where the function concaves up and where it concaves down. So the first thing is to solve the bullet number one. So Roman figure number 1. So we'll end up having, what is the first derivative with respect to x of this? It's going to be 4x to the power 3 minus 8x, because 2 times 4 is an 8. Then we have that, and then the second derivative with respect to x is going to be, I'm going to multiply this with that. 3 times 4 is a 12x, subtract a 1, we have a 2 minus an 8. This is actually the same as 12 and 8, 4 is common, so we'll end up having x squared minus a 2. I think that's gonna be it, because 4 times 2 is actually going to be, this is not correct. Here we'll have a 4 because it's common, and then 12 divided by 4 is supposed to be 3x squared, and then this one is going to be a minus 2 as a second derivative. The second thing that we wanted to actually do here, we want to set the second derivative equal to 0. So we'll have 3x squared minus a 2 equal to 0. Divide by 4 on both sides, and then this one will end up having 3x squared minus 2 is equal to a 0. 4 divided by 0 divided by 4 is a 0. And then here, because here literally speaking I cannot actually I can, I'm going to take this minus 2 to the other side, so it's going to be positive. I'll be having 3x to the power 3 is equal to 2, and then I divide by 3 on both sides. Of course, this 3 and that 3 will cancel out. I'll have x squared is equal to 2 over 3. And then after that, I take the square root on both sides, so I'll end up having x equal to plus or minus the square root of 2 over 3. So I have that. And then once I have those two values, I want to place them on a number line. So here I will have minus 2 over 3. Here I am going to have this is a square root of that, and you have a square root of 2 over 3. So we're actually having these two things. And then the next thing that we wanted to actually deal with here, I want us to actually realize something, that the second derivative with respect to x is equal to, it was equal to 12x squared minus 8. So we have 12x squared minus 8. I think that was original. X squared minus 8. And then I want a number that is less than this. Most of the time you don't have a calculator, so to get a number that is less than this, I know for a fact that minus 10 is less than this number, and the number in between a negative and a positive I know is going to be 0, and the number above this I'm going to pick a 10 because I'm not for sure that 10 is bigger than the square root of that. I don't know this, I don't know that. So when you don't have a calculator, you usually pick those numbers that you are sure of. And then if let's say I'm saying this one here minus a minus, and then I square it, I'll get a positive, and 12 times and 10 squared is going to be 100 times 12 is going to be 1200. So 1200 minus 8 is going to be positive. That is what is important, it's positive. But if I pick a 0 and plug it here, I will get a 0 here, and then 0 minus 8, I will get a minus 8. So here I will end up having a minus, and then I'm plugging a 10 again here. 10 to the power 2 is going to be 100 again. 100 times this is going to be 1200. 1200 minus that's still going to be a positive number. So that is what is important here. Plug this in the second derivative, and then plug this in the second derivative to actually see if I'm getting a positive or negative. And take note that at this point and at that point we don't include those two. So if you look here, because we're moving from negative infinity to positive infinity, so if we are at negative infinity and we're going to negative square root 2 over 3, so we have negative square root 2 over 3, and also moving from negative square root 2 over 3 and then to positive square root 2 over 3, and then we're also moving from square root 2 over 3 up to positive infinity. What is happening? So you can see that we have a positive here, which means concave up. So here f concaves up because the second derivative is positive, and then in between here you can see that f concaves are down because we have a negative there, and then here we're actually having because we have a positive again, so we have concave up. So that is what is important here. Any point here, you can see these are the intervals that were expected, so we've classified them. And then the next thing that we wanted to talk about is use the second derivative test to classify the critical points. First, let's find the critical points. In other words, what is the first derivative with respect to x? The first derivative with respect to x, it was 4x cubed minus 8x. So it was, let me see here, the original function f of x it was equal to x to the power 4 minus 4x squared. So I said that this one here was supposed to be 4x cubed minus 8x. So that was the first derivative, and I said that this can be factored because 4 and 4 is a common factor, and we have an x, and then here once x is taken out of, say, x cubed divided by x, 4x cubed divided by 4x is going to be just an x squared minus, and then here I end up having a 2 there because 8x divided by 4x, x will be gone. 8 divided by 4 is going to be a 2. And now the next thing is you want to set the first derivative equal to 0. So you have x squared minus 2. I want this to be equal to 0. In other words, I want 4x to be equal to 0, or x squared minus 2 to be equal to 0. And then if you take note of this way, this one can only be equal to 0 if I divide on both sides by 4, and this one I will have x squared is equal to this was minus, so on the other side is going to be positive 2, and then if this 4 and this 4 will cancel out, and now you will have x is equal to 0 divided by 4 is 0, or x is equal to plus or minus the square root of 2. So we are having this and those two. Those are the critical numbers. So you draw a number line, if the question was saying use the first derivative test, we're going to draw a number line, but now it says use the second derivative test. In other words, use this information that you already know about concave up or down, and then conclude without the number line that we actually use for the first derivative test. So the first thing that you need to know here is that if x is equal to 0, so if x, let's say x is equal to 0, what is going to be our y? If x is equal to negative square root 2, what is going to be our y? If our x is equal to positive square root 2, what is going to be our y? That is actually the next step. So our original function was saying that we are having x to the power 4. So we're having x to the power 4 and then minus 4 or x squared. So if we are having a 0 here and a 0 there, we know that whatever we're supposed to get is a 0. So here we're having a 0, 0, and then if we're having a negative square root 2, and then here we're having a negative square root 2. So what is going to happen here? We'll end up having a minus 4, and then if we are having a positive square roots, we're still gonna end up having a minus a 4. So the question is, if you look at 0, 0, 0, you can see that 0, 0 is somewhere. That's what is important here. This one is negative, this one is negative, and this one is negative. So there is no way that you can have 0 in between two negatives. So this one is negative and this one is positive. So 0 must be in this interval. And this interval is saying we have concave down. So we have concave down here. So we have concave down. Concave down is like this. So 0 is somewhere there. Therefore, this one is a local max. So we have a local maximum, because we have concave down. And then we look at this point, both these 2 points are negative. Okay, this one here, this x value is negative. So we go and look at these intervals here. Where is it negative? So we have this one, negative root 2. Where is negative root 2? So if we look at negative root 2, you can see that negative root 2, is it here? Is it there? Is it there? one thing for sure, this is positive and this one is positive, therefore a negative root 2 cannot be here. And also, if you look at this number, negative root 2, so if you were in a number line here, you can see that if I have here root 2, right, I have root 2, and I know negative root 2, I know that I have negative root 2, and then I divide this by negative root 3. Is this number less than or bigger than a 1? So if this number is bigger than a 1, this number is actually getting smaller. Otherwise, it's supposed to be this side. So minus root 2 over 3 is actually this side, not that side. So negative root 2 is not here. It is there where we are having concave up. So here we have concave up. So concave up is like this. So this point is somewhere there. So we have a local mean. So we have a local minimum. And then when we look into this one is positive. So if it is positive, it must be in this interval between two positive numbers. So positive numbers are telling us that we have concave up. So concave up is like this. So this point is somewhere there. So we are also having here a local minimum. That's how you end up solving this particular question. Let us try and see if what we are saying is it true, is it not true. So we are having a function here, and our function is nicely saying to us that we have this is x to the power 4, and then we are subtracting 4x, and then are we having an x squared? Let me double check here in our question. So here we are having this one here is x to the power 4 minus 4x squared. So we're having that. So this is what we're actually having. You can actually see in this function that we are having a local mean here and a local mean. So we have two local mean and we have a local max at 0. So what we are actually having here, we have a local max at 0, we have local mean. So that is what is important. So we have a nice function like that. So we are actually still on a point on actually finding where we're having local max using the second derivative test. So we move to another question now, which is number C. Number C is saying we have f of x, and our f of x is equal to x to the power 5. This function here, I do want to, part of me want to skip it because it's straightforward, but let's do it. So Roman figure 1 is saying find out where the function concaves up and where it concaves down. So we have f prime of x is equal to 5x to the power 4, and f w prime of x, it is equal to, this times that is going to be 20x to the power 3, and then 20x to the power 3, we want to set it equal to 0 so that we can get the x coordinate of the point of inflection, or the point whereby concavity is changing. So this one, and then I divide by 20 on both sides, and then I will end up having x cubed is equal to 0, and therefore x is just going to be 0 because x times 0, x times x times x is equal to 0. That can only happen if this is equal to 0, or you can say that we have x is equal to the cube root of 0, and you know that the cube root of 0, which is that, is going to be a nice 0. So that's what is actually happening. So we are having an x equal to 0 here, which is actually telling us that this function here is actually going to have the second derivative equal to 0 if x is equal to 0. And then once you have that, of course, the second thing that we wanted to look at, what was the initial question? And the initial question is said that find the interval where the function concaves up. So this one is the x coordinate of the point of inflection. So what does that mean for us? It means that the next step that we need to actually end up having here is to take this and place it in the number line. So we have a 0 here, and also have negative infinity this side, and we have a positive infinity this side. So if you actually look into this, the next step will be pick a point less than 0, which is -1, and then you plug it here. So if I'm plugging in here a negative 1, negative 1 times negative 1 times negative 1, we will end up having a negative. Of course, times a 20 is always going to be a negative here. And then here, if I'm plugging in a positive 1, I'm going to take a number bigger than 0, which is 1. And then 1 times 1 times 1 is still going to be a positive 1 times a positive 20 is going to be a positive. Of course, at this particular point here, you can actually see that we are actually having nothing. There's no change at this there's nothing happening at that particular point. Or if this one was concave down, it is changing to concave up. If this one is concave up, it means that at this particular point there is a change of concavity. There's nothing that is actually saying we have concave up or down. There is a change that is happening at that particular point. And then now you can actually see that from negative infinity up until you arrive at 0, something is happening in f. And if you're looking at 0 up to positive infinity, you can see that something is happening at f. Of course, when you have a negative here, it means that f are concaves are down. And then when you have this one positive, it means we have f are concaves up. So that is basically the point. So we have a nice function. You can see that function, we know that it is something of this type. So this one is kind of saying that we have concave down, and then we start to have concave up. So that is what is basically happening there. Now we have intervals for concave up and concave down. And then we want to talk about Roman figure number 2. And Roman figure number 2 is saying that use the second derivative test to verify or to actually classify the critical points. The question is, what was the first derivative with respect to x? And you can see that the first derivative here was actually 5x to the power 4. So we have 5x to the power 4, and you want to set it to be equal to 0. So you have x to the power 4 equal to 0. And then after that, you divide by 5 on both sides. And then after that, you will get x to the power 4 is equal to 0, and which means that x is just equal to the fourth root of 0, which is just 0. So our x is equal to a 0. So if I take this 0 here, so I have my x equal to 0, and then I want to find out what is going to be our f of 0. So if I go to the original equation, which was this, and I plug in a 0 here, I will get 0 to the power 5 or just a 0. Now we wanted to actually find out if is this a local mean, is this a local max, or is it neither. So we look at this point here, which is 0. So we look for the x value. So is this x value in this interval, or is it in that interval, or is it actually not in any of these intervals here? So if you look at 0, because we don't have a square here, we don't have a square bracket, which means 0 is not included in this interval. And if we are plugging in, we're looking for 0 in this interval, you can see that we don't have a square bracket here, because 0 is not included, because at 0 we know that we don't have a concave up or down. There is a change that is happening there. So when you look at this 0 here, 0 is not part of this interval, 0 is not part of that interval, which means that this interval here, nothing is happening. So you can say that this point here is we can just say f does not have a local a local maximum and f does not have a local minimum. So you have minimum at this point, so we are actually having this. So for this particular case, you can actually see that function actually, what is actually happening is actually there is a change of concavity, but there is no change in increase to decrease. So at that particular point, you can see that it's neither the max is there or the mean is there. And then we have our D now. What is our D saying? It's saying we have f of x is equal to 1 over a 4 x to the power 4. 1 over 4 times x to the power 4 minus x squared. Of course, here we want to find where it changed concavity. So we have to find the first derivative with respect to x, and when we're multiplying 1 over 4 by 4, we'll get a 1. So this is going to be x to the power 3 minus 2x, and then we find the second derivative with respect to x, and we get 3x squared minus a 2. So we have this nice thing here, and then we set it equal to 0 to find the x coordinate of the point of inflection. So we set it this equal to 0, and then take this to the other side. So we have 3x squared is equal to positive 2, and then we divide by 3 on both sides. So we have x squared is equal to 2 over 3, and then we take the square root on both sides. So we'll have x is equal to plus or minus the square root of 2 over 3. So that's what we end up having here. So once you have these points, of course you wanted to have a nice number line, and then you will end up having minus square root of 2 over 3, and then the other point is going to be here, which is just the square root 2 over 3. This is positive, this is negative, and also these points are not included because that's where the change is actually happening. So they are not included, and this number line is moving from negative infinity to positive infinity. So if you look into this, I wanted to pick a point here that I know that it is less than this, so I'm going to pick a minus 10, and if I'm plugging in a minus 10 here, I will get a minus 10 raised to the power 2 is going to be 100. 100 times 3 is going to be 300. 300 minus 2 is going to be positive, so we have a positive here if I'm taking a minus 10, and this is minus, this is positive, so 0 must be in between. So I take this 0, I plug it there, and then when I'm plugging it there, this whole thing will go to 0, and we have a minus 2, so this is going to be minus, and then I'm plugging in a 10 that I am sure it is bigger than this. So when I'm plugging in a 10 here, 10 squared is 100, 100 times 3, 300, 300 minus 2 is going to be 298. So this one is still positive. What does this mean? The second derivative is actually positive in this interval. The second derivative is negative here. The second derivative is positive here. In other words, if I am moving from negative infinity to a negative square root of 2 over 3, what does this mean? It means that from this interval, I know that the second derivative is actually with respect to x is actually bigger than 0 or positive. And then if that is the case, it means now when you're moving from negative square root of square root of 2 over 3 to positive square root of 2 over 3. So this one is actually telling us that the second derivative with respect to x is less than 0 because it's negative. And then the last interval is actually telling us that if you are moving from the square root of 2 over 3 to positive infinity, we know that the second derivative with respect to x is bigger than 0. What does that mean? If the second derivative is bigger than 0, which means that f concaves, because bigger than 0, so it means concaves up, and then this one f concaves down because it's negative, and then this one here is actually telling us that f concaves because it's positive, so it concaves up. So that is what this thing is actually telling us. And then the next thing that we wanted to do, because I wanted to classify, are we having concave up or down? So in this interval and that interval we have concave up, and in this one we have concave down. And then now the next thing that we wanted to talk about now is analyzing the critical points. So what is important about the critical points is this: we wanted to first find the first derivative of this function. That is what is important. So the first derivative of this function is supposed to be x to the power 3 and then minus 2x. That is what this thing is all about. And also I can factor out x here, so I can say that this is the same as just x, and then I have x squared minus 2. So that was the first derivative. Let me double check here. So the first derivative was actually this one here. So once you are having the first derivative here, you can see that to find the critical points, you actually want to set the first derivative equal to 0. So I have x and I have x squared minus 2. I want this to be equal to 0. In other words, I either have x equal to 0 or I have x squared minus 2 equal to 0. So x is equal to 0 or x squared is equal to a positive 2. So once you are having this, we need to solve this. In other words, I take the square root on both sides, so I'll end up having x equal to plus or minus the square root of 2. So once you are having this nice thing here and that one there, we are actually saying that now we already have these critical points, 3 of them, negative, positive, and that is 0 there. So the next thing that you need to do, what actually happens if x is equal to 0? So I have 0. What is the y? And then if x is equal to a negative square root 2, what is the y? If x is equal to the square root 2, what is the y? Now I take this 0 and I plug it in the original function, which was f of x is equal to 1 over 4 x to the power 4 minus x squared. So if I'm plugging in a 0 here, this whole thing will be 0. Plugging in a 0 here, this whole thing will be 0. So the y value will be 0. If I'm plugging in here minus square root of 2, so I have 1 divided by 4. And then here I will end up having a negative square root 2. And then I can square it up. No, this is supposed to be 4. And then after that, I wanted to minus and then a negative square root of 2, and then I'm gonna square it up. So this one I wanted to square it up. So the answer that I'm going to get here is going to be minus 1. Of course, this is x, this is the power 4, this is the power 4. So if this is negative, it's going to be the same as positive, and this one is still going to be the same. So here we'll still end up with a minus a 1. So that is going to be the output there. So the next thing that I want us to do, remember that if we're using the first derivative test, we're just going to look for the number line of the first derivative of this. But the question is saying use the second derivative. In other words, if you know that the second derivative is positive in this interval, what can you say? Are we having a local mean or a local max? So you go to these intervals here, and then we have a 0 here, x, this is x. Remember that these points here, we have x and y. So we only focus on the x. So you go here, this interval are the x intervals. So these are the intervals. So 0 is between a negative and a positive. This one is negative and this is negative, so 0 cannot be here. But here this is negative, this is positive, so 0 is in this interval. And in this interval, f concaves up. So if f concaves up, it means that it is like this. So f concaves up. So if f, no, where are we? Here. So we have f concaves down, so we have concave down. So f concaves are down is like this, so this is concave down. So the point is somewhere there. So this point here is maximum because this is the largest point that you can have here. If 0 is here, so we have concave down here, which means 0 is a local max. So here we are actually having a local maximum. So we have a local maximum. And then in this interval here, this number here, negative 0.2, is negative. So if it is negative, it cannot be in this interval because both these numbers are negative. So it can either be here or there. But when you look at the negative 2 is on this side of this one here. It is way less than this because this one is divided by 3, so it is actually getting closer to it. This one is closer to 0 compared to a negative square root 2. So a negative square root 2 is somewhere in this interval here. So if it is here, f concaves up. If it concave up, it means f is like this, and then the point is somewhere there. So if the point is somewhere there, this is the smallest value this function have close to this point. So we are actually having a local minimum. So here we are actually having a local minimum. So we have a local minimum. And then in this interval here, we have a positive square root 2. The positive square root 2 is between these two positive numbers. So if you look into this one here, we have concave up, and concave up is somewhere like this. So we're actually having a number that is there. So this one here is actually going to tell you that you are actually having a local minimum. So that is what is important here. You can even check it the same way we did. We had where's this? We had this. So here we can say that we want to check what is basically happening. So you have y, and your y, we want it to be equal to 1 divided by 4, and then of course you have x, and then you raise this to 4, and then after that you subtract x squared. So if you look into this one here, let me double check if we are having this function. So this function here is this one, 1 over 4x to the power 4 minus x squared. So we're actually having a nice function here. So this point here is actually telling us that we have at negative square root 2. You can see that at negative square root 2, negative square root 2, we have a local minimum, so there is a minimum there, and a positive 2, we have a local minimum, and we have a max at 0. That is what is happening there. So it's one way to actually find this one out using the second derivative test. The last question now is this one here. We have f of x is equal to the natural log of x squared plus a 1. So we have our E now, which is the last question. Then we can call it a day. So we have our f of x is equal to natural log of x squared plus a 1. Of course, the first question, you want the intervals where the function is increasing and where it is actually where the function concaves up and where it concaves down. So the first thing to do, you want to find the first derivative with respect to x. You know that if our f of x was actually equal to the natural log of x, the first derivative was actually going to be equal to 1 over x. So if we were to treat this part as just x, we're supposed to end up having 1 over x, in other words 1 over x squared plus 1, and then now we have to take the derivative of that inside function, which is x squared plus a 1. We used a chain rule here, but this is just using a shortcut. So when you look into this, we're actually having 1 divided by x squared plus a 1, and the derivative of this is just gonna be 2x plus the derivative of a constant is always going to be a 0. So we're actually having a 2x divided by you have an x squared plus a 1. And then we're actually having now this as f prime of x. And if you look carefully into this one here, you can realize that it is the same as 2x times x squared plus 1 raised to minus 1. This minus here is just telling us that this was in the denominator. No, this was the first derivative, not the second. So if you wanted to find the second derivative, you have to take the derivative of this particular functions, either this or that, depending on what you are comfortable with. If you wanted to you take the derivative of this, you will end up using the quotient rule. But if you are using this one here, you will use the product rule plus the chain rule. So what I'm going to do here, I'm just going to use the one that I see and I know it is very, very, very easy for me. Okay. Which one is actually easy? I think this one actually is the one that we never did used before. Or let me use the quotient rule so that you don't forget it. But this one is one easy way to use product rule plus the chain rule. It was going to be easy here. So let's use the one to find the second derivative with respect to x. Remember what we said. We have low d high minus high d low. Low d high divided by low. So we have low, so we're gonna take the denominator as it is, so we'll end up having x squared plus 1 times the derivative of the numerator. So we take the derivative with respect to x of the numerator, which is 2x, and then minus 2x times the derivative with respect to x of the denominator, which is x squared plus a 1. And then after that, I'm going to divide this whole thing by the denominator squared plus 1. I hope you still remember this, and then you square it up. And then if you look into this one here, you will find out that you're actually having x squared plus 1 times, what is the derivative of 2x? It's just going to be a 2 minus 2x, and the derivative of this, we know that is still going to be a 2x. And then you divide this whole thing by x squared plus 1 all squared. And if you simplify here, you will end up having 2x squared. So it's 2 times this is going to be 2x squared plus 2 minus 2x times 2x is going to be actually 2 times 2 is going to be 4. X times x is going to be x squared all over. I have x squared plus 1 all squared. And then this whole thing is going to tell us that I have 2x squared minus 4x squared. So I have minus 2x squared plus a 2. And then all over x squared plus a 1 squared. So there is absolutely nothing that can be done to actually simplify this, and whether you try it or you don't, you're still gonna end up with something that is of this type. So we have the second derivative with respect to x is equal to this, and then once you are having the second derivative equal to this, now we started to set it equal to 0. So we have minus 2x squared plus a 2 all over x squared plus 1. We want this to be equal to a 0. When is this thing gonna be equal to 0? Remember that if the denominator is equal to 0, this whole thing is going to be undefined. So this is going to be equal to 0 if the numerator 2x squared plus 2 is equal to 0. So I'm gonna take this 2 to the other side. So I have minus 2x squared is equal to, this was positive, so in that side it's going to be negative, and then I'm going to divide by negative 2 on both sides, and then when I'm dividing that, I will end up having x squared is equal to, and then this will cancel with that, so we're left with x squared, and then we will end up having x minus 2 divided by minus 2 is just a 1, and then we can actually end up taking the square root on both sides. When we're taking the square root on both sides here, you will end up getting, remember that this is the same as the absolute value of x is equal to, this one is just a 1. So if the absolute value of this is equal to 1, which means that I have plus or minus x is equal to 1, right? So that I actually have x is equal to plus or minus 1. So that is what we are actually having here, or you can factorize right away. So I'm just saying that this and that is just the same thing, and this actually means plus or minus must be equal to that. And then the next thing that we're actually having here, we have these points here. So we're supposed to actually start with the number line, but now we have to check what are the values of x that will make this whole thing undefined. In other words, when will this thing be actually the denominator equal to 0? So you can see that here, in order for us for the denominator to be equal to 0, we need x squared plus 1 to be equal to 0. And if you have x squared equal to minus 1, you can see that you are actually having imaginary numbers, because you will end up having x is equal to plus or minus the square root of a negative number. So you have imaginary numbers. In other words, the denominator can never be equal to 0 in this particular case, so that the only values we have is when the denominator is equal to when the numerator is equal to 0. In other words, when x is equal to minus 1 and when x is equal to a1. And then the next thing, remember that our f prime w prime of x, it was equal to negative 2x squared plus a 2 all over x squared plus 1 all squared. So that is actually the second derivative with respect to x. So the next thing is, I want to pick a value that is less than negative 1, which is, let's say, negative 2, and then I take this negative 2 and then I plug it here and see if I'm getting a positive or a negative. I pick a value between negative and positive, which means 0, and a value that is bigger than that, which is 2. So if I'm starting with 0, if I plug in a 0 here, this part is going to go to 0. I'll be left with a 2. In other words, I will have a positive in the numerator. And if I'm plugging a 0 here, I will be left with 1, and you square it up, I will get a positive. So here, a 0 is actually telling us that we will get a positive, because a positive over positive is a positive. If I pick a negative 2 here, if I take a negative 2 and I'm plugging it here, negative 2 raised to 2 is a positive 4. Positive 4 times a negative 2 is going to be a minus 8. Minus 8 plus a 2 is going to be a minus 6. In other words, in the numerator, we'll have a negative. And then after that, I go here. If I plug in a negative 2 and I square it up, I'll get a positive 4 plus a 1. I will get a positive 5. And then square it up, I'm still going to get a positive. So in the denominator, I will get a positive. So negative divided by a positive is going to be a negative, so we have a negative here. And then if I am plugging in here, let's say I'm plugging in a positive 2. Positive 2 squared is 4. 4 times minus 2 is going to be minus 8. Minus 8 plus a 2 is going to be a minus 6. Of course, it's a minus. And then I'm plugging in here. Whether it's positive or negative, I have this square here. Whatever the answer that I will get here, I will square it up, I will get a positive. So I have a negative divided by positive, so I will have a negative. What does this mean here? Because we're moving from negative infinity to positive infinity, it means that for values that are between negative infinity and negative 1, we can see that we are having fw prime of x is actually less than 0. In other words, it's negative. And if I'm looking for values that are negative from negative 1 to 1, it means that fw prime of x, we are actually having a positive here, which means it's greater than 0. And if we're looking for values from 1 up to positive infinity, we have fw prime of x and it's negative. And if the second derivative is less than 0, it means that f concaves, if this one is less than 0, which means it concaves are down. And when we are actually having f bigger than 0, which means we're actually having f concaves up. And then of course here less than 0, it means f concaves down. So that's how you actually use this second derivative to check concavity. And then now we go for the second part here. The second part is actually telling us that use the second derivative test to classify the critical points. So first we need to find the critical points. What was the first derivative? Because to find the critical points, we want to make the first derivative equal to 0. So we are actually having, where is this? So the first derivative is 2x divided by x squared plus 1. So we are having the first derivative 2x divided by x squared plus a 1. So we wanted to set this thing equal to 0 to find the critical points. So if we have x squared plus 1, and of course we want it to be equal to 0. And for this thing to be equal to 0, we want the numerator to be equal to 0, because if the denominator is equal to 0, we'll actually end up having an undefined. So the first thing, we set the numerator equal to 0. In other words, I divide by 2 on both sides. I will have x is equal to a 0. So we're having that. And now we ask ourselves, what are the values of x that will make this undefined? In other words, we want to find f prime of x. This one was when f prime of x was equal to 0. Now this one, we want it undefined. For this thing to be undefined, we want the denominator to be equal to 0. In other words, x squared to be equal to minus 1. In other words, x to be equal to plus or minus the square root of minus 1. But when you are looking into this thing here, it's actually telling us that we have an imaginary value. In other words, this function here, let me write it with this one here. F prime of x will always be, this is not always, will always be defined. Will always be defined because when we're trying to solve for x, we are getting an imaginary value. So which means that the denominator can never be 0. In other words, this will always be defined. That's what I want you to actually get. So we are actually having only this value here, which means now when we are having this is the only critical value. If we were using the first derivative test, we were going to draw the number line for this, but now the question is saying use the second derivative test. In other words, use the information that you actually have here to determine if are we having a local max or a local min. So if x is equal to 0 here, take note that we had our f of x. Our f of x in this case was the natural log of x squared plus 1. So if x is equal to 0, 0 squared is going to be a 0, 0 plus 1 is going to be 1, and we know that ln of 1 is just the same as 0. So we have 0 over 0. Now, I want us to classify this point. Take note that this is x, this is y. And I also want you to notice that this is not x and y, these are the interval. So x is between these values, these are intervals. But this one here is actually the coordinate. So we look at this x coordinate and see if which interval does this x actually belong in. So if you look here, we have 0. 0 here, this one here is 1 to infinity. So all the numbers that are here are positive. So 0 is not bigger than 1, it is less than 1, so it cannot be here. But if we look for this one here, we have 1. So 1 is bigger than 0. But negative 1 is actually less than 0. So 0 is in between these two numbers. And between these two numbers, we have concave up. So we have concave up. Concave up is like this. So actually, at 0, we are actually having a local. So we have a local minimum. Why are we having a local minimum? Because concave up is like this. So this point that is here is actually the smallest that is actually available. So that is how you actually use the second derivative test to actually classify a critical point. And of course, we can try and test this whole thing here and see if we made a mistake. If we made a mistake, we'll check where did we actually make a mistake. But if we did not make a mistake, then we don't have to check anything. So if we have, let's say, a natural log of we have x, and then we want to square it up, and then after that we want to end up adding a 1. What are we actually having? What is this looking like? So if you look into this function here, you can see that it's looking nicely, and it goes all the way, and then it goes up nicely. And if you look carefully in what we found, we actually found out that at this particular point we're having a local minimum. This is a local minimum, so that is actually how you end up dealing with these problems. Again, this app here is what I usually call it GeoGebra Classic, and GeoGebra Classic actually helps you to plot. There are other things that you can use, even Desmos. Usually, sometimes we use this one to. Where is this now? Why is it not doing anything? So sometimes we usually use Desmos. So if let's say you are just using this one, Desmos, so you will find out that you are having something of this kind, and you click to it. It will start showing. It's supposed to start showing some functions here. Where is this now? So we wanted the graphing calculator, so you click there, and then you can just write your function that y is equal to the natural log, and then of course you're gonna end up having x, and then you go up and then you place the head to say that you have an x squared, and then after that you can start saying +1. This is also another software that we usually use, but the reason I am using, you can see it can actually give you that point exactly, and when you're looking at that point it gives you exactly. When it's giving you that point, it actually gives you a nice point. And if you look at the other one that we have, I think it was e, and then we raise it to a minus x, and then we raise that to a squared. You can see actually it also give you that point nicely, and the other points it can also give you in a nice way. And also another thing that is nice about this, if you want to place some arrows, you can place some arrows, and if you don't like the grid lines, you can remove them. If you want to add them, that is also nice. Those are the things that you can actually use with this. If you want to zoom in, you can zoom in. If you want to zoom out, you can zoom out. The reason I usually like this is because I like it because it has that interesting spreadsheet that I usually use to this one here. If let's say I wanted to actually convert points and approximate using a graph, I usually use this one. It's a nice tool to use. Of course, I'm going to end up there. Try and do these questions and practice and see what you are actually getting, and then from here we will focus on optimization and see how can we actually deal with optimization problems, and then from there we go with integration. I hope you will understand, because integration actually follows directly from the understanding of derivatives. And if you can see, if you want to take a derivative of this function using the chain rule, I want you to notice that we take this as, suppose it was natural log of x, whereby you have 1 over, and then whatever is inside is what goes to the denominator, then you take the derivative of that. And once you notice the derivative of this, it will be easy for you to take the integration of certain functions. I'm going to stop there. Hopefully you actually learned a lot from this.